Finally, I'd like to thank LIACC for granting me the opportunity to be here. Okay, so some background on algebraic subtyping. A couple of years back, Stephen Dolan presented MLsub, which he had developed along with Alan Mycroft. MLsub is a minimal ML language with that combines algebraic subtyping with parametric polymorphism. The interesting result of MLsub is that it can infer principal types that are still compact in the sense that usually subtyping algorithms they either don't give you principal types or they give you a type with a long list of constraints attached to it, and they manage to simplify that by using intersections and unions instead of constraints. But MLsub was complex. I can't really understand his thesis. He uses a lot of abstract algebra and polar types, unification, which is unification on polar types. So a few years later, Parrot, who's probably watching, he presented an alternative algorithm, SimpleSub, where he claims that none of those abstract algebra notions are interest to the type inference phase of the algorithm. His algorithm is much closer to Hindley-Milner type inference, and so it's very much easier to understand. I believe that the simplification phase of that algorithm is still a little complex, and I had some trouble with that, but it's a very good algorithm and a good base to work on. So what's algebraic subtyping? In MLsub, we have all of the usual constructs from ML. We have variables, abstractions, functions, function application. We have records, and we have the same types. We have functions and record types, type variables. What he introduced, though, is top and bottom types and intersections and unions. Those are necessary to give principal types to the sum terms. An interesting thing about unions and intersections is that intersections can only appear in input positions, so as arguments to a function, and unions can only appear as output to a function, so that restricts the expressiveness of the system a bit. And the only thing he does to extend the type system is that the subsumption rule. But let's focus on records for now, as that is the topic of the talk, of my presentation. So in MLsub, a record type with field X as type int subsumes all the records with at least that field, which means that we can use it. We can use a type like that to infer a type for example, the polymorphic selection, where we give it the type X as a file field X as type alpha and returns alpha. But with subtyping alone, that's the notion that, so that means we can pass it any record of any size as long as it has that field X, which means we can kind of forget the fields that are there already. So as you can see in the example, we have a colored point is a subtype of a point. MLsub has the usual subtyping rules. Depth is defined on the single field records, because records are equivalent to intersections of field types, and that is how width is defined using intersection. But MLsub lacks the record expansion operation, which is an operation you can use to add a new field per record. So in this example, we have the record, a point record, and we paint it blue, and we get a record with another field. With only subtyping, we can't really give this operation a precise type. So it takes a record, it takes a value, and it returns a field with that value, which is the record type which at least has that field. We forget about the fields we had before. So if we try to, for example, with the point, if we try to select the field X, we don't know it anymore because we only know that it at least has the type Y, the field type Y, which is an int. The usual solution to this was row polymorphism by Wand and Remy and other authors. Row polymorphism introduces row variables to the language, which stand for, all the fields you don't really know about, and you can collect constraints on that on the previous fields using those variables. So with row polymorphism, the same operation will have the type row and the alpha, and it will still have the alpha and the row and the same row. So all the same fields it had before. With row polymorphism, now we can constrain row to have the X as type int, and the previous term becomes typeable. So to extend MLsub with row polymorphism, we have to change the type system a little bit. We change records to be built upon by rows. So we start with the empty record, and we keep building, well, apps in this case, but we keep pulling on from that. We have apps. Yeah, we will love from that. As you can see in the row type, a row is just a field plus the other row and so on. But it can also be a variable, which we use that too. So we don't only do extension, we also do modification. So we allow rows to be variables, which turns out to be useful. One point of contention, though, is the necessity of the presence flags. Remy noted that they are essential for principal types using row polymorphism. But in my prototypes, I've had, well, we'll see. So we have the extension rule, which it says we have a term which should be a record with the field. We say that the field L can be a variable because it can be either present or absent, or we don't care. We just want to have it there so we can have some constraints on it. And we also track the row, so we can have information about any previous records. The type of the value we're adding is just not very important, so we have present tau. Selection is the same, we just use the present. It's the same as before except for the present tag. The subtyping relation is, well, it changes quite a bit because now we have to introduce rows. Records are now defined on rows, so we lose some of the properties we had before. So we introduced the unfold relation, so we can have an equivalence between the empty. Well, we can always keep adding labels that are absent. That is always equivalent to the previous type. So if you have the point type X and Y, if we say that color is absent, it's still the same type. We use commutativity because we lost the property that rows are partial functions from labels to value to types. So now we have to reorder them. The ignore relation is used instead of the previous forget operation, so we can still type selection. Well, so we can still forget about not select, so we can still type records, so we can still ignore the other fields that we do not care about. Pre is covariant, and okay. So for type inference, we need an important concept that is row expansion expansion from Potier, and that is when we have a constraint of the form x as type tau. We have a field x with type tau and many other fields, and that is smaller than a record with a different fields. Well, this can only be true if x is present on the other side, on the right hand side. So to solve this constraint, we create an expansion from row prime to we insert x in row prime, and we create a new fresh row variable for that. We say that x is an alpha because we don't really know what it is yet. We also constrain tau and alpha and the row variables. So that was probably pretty confusing. So I'm going to try to walk through an inference example. We have the term lambda r. We have the function that receives a record and returns and extends it with the field y. We start by creating the fresh variable alpha for the record, for the input. We have the extension. So the extension, we constrain it. We constrain the record being extended by y as any type and row for the previous fields that it might have. So we have the constraint alpha is less than that, and the resulting type for the extension is the y field is present and the row variables, the row is still there, the previous row is still there. The full type for this term then is it receives an alpha and it produces that. We can apply the coalescence from simple sub to say that we receive a record that we don't know what the y variable field is, and it has some other fields contained in the row, and it returns a present y field. Here I'm not using the present because it's not necessary to visualize that, but it's there, and it still has the same row as before. Okay, so let's type the application with that. We're clearly passing a record with type x as a type int. Can I have sorry? Okay, so the full application. The application obviously constrains the left field as the function that receives the type of the lambda and returns the type of its body, so alpha in the y as type int row, and we constrain that to the function that receives its input. So sorry, 1 minute left.
If you want some questions,
That was fast. Well, we can skip ahead. What we care about is about the row expansion. So where is that? Okay, so when we constrain the type of R to be the row that it's receiving, it becomes a lower bound of alpha. But alpha already has an upper bound, so we also constrain that, which means, and we the row expansion case, so x is missing from the right hand side. We create the expansion from rho to x as type gamma rho prime, sorry. We apply that expansion and we get this constraint. So int is the lower bound of gamma, and that is important because if you remember, oh, right, I missed the function variance and contravariance, but oh well, I don't have time. We are on the right hand side. Oh, so the we are on the covariant side of the function of the constraints. We still have the row. So we have to expand that. We get the x back, and we can say that it returns the type we want. And I guess it's over.